All right, hey guys. Today we are broadcasting from Spain in my hotel room. I'm at the NIPS conference. I got something like 3 hours of sleep on the red eye over here, but I'll try and make sense despite that. So today we're going to do discrete optimization. And then the other thing we're going to do today, we're going to try and leave some time at the end of class for questions. And so if you guys can think of questions during class, and post them on Piazza. I'll try and go through Piazza and spend some time talking about any of the questions that show up there during class. So post things that you think would be good to talk about during class instead of just having me type up an answer later. All right, so here's, let's get back to the slides. Okay, so discrete optimization. So we've been doing continuous optimization for a little while, and discrete optimization is the same idea but harder. Basically, what discrete optimization is when the variables are categorical or binary instead of continuous. And I'm also going to talk about mixed optimization, which is where you have both continuous and discrete variables in the same problem. So let's start with a couple of examples of why you might care about doing discrete or mixed optimization. One of them is outlier detection. So in outlier detection, we can keep a binary random variable that says whether each one of our examples is an outlier, and then we can try to maximize the fit of our regression model to the inliers, and then maybe have a small penalty for every variable that we declare to be every example that we declare to be an outlier. Another example is a mixture model. So a mixture model means that instead of learning a single model that fits all of our data, we split our data into subsets and fit each one of the subsets with a different model. And we have the continuous variables for the model parameters like we did before, but then we also have discrete variables that tell us which one of our models fits which one of our data points. And to go into a little bit more detail, one common mixture model would be a Gaussian mixture model, where your model is a Gaussian, hence the name. So the idea is that instead of fitting one Gaussian to all of your data, you'll fit several. So if your data looks something like this, right? So you have, right? So if your data looks like that, right? A Gaussian might be appropriate, but if your data, has another group of points over there, that doesn't look so Gaussian, right? Especially if you've got like sort of extra density in the middle here. And so you might want to fit two Gaussians to this data. One Gaussian, let's say that they're spherical covariance, so the only thing that you have to fit is the mean. So you could put one mean right there and another mean right there, and you would presumably do a better job modeling this data with these two Gaussians than you would with just one. And then you would split the data, right, halfway between the two means, and assign all of the points over here to this Gaussian, all the points over here to that Gaussian. Or you might do a soft assignment where it sort of gets fuzzy around the boundary. All right. Oh, and I should mention as well that this outlier detection model that we talked about up here, that's also a mixture model. You can think of it as a mixture between a regression model, where you fit all of your inliers with a regression model. I'm getting lagged now. Let's see. It seems like the lag is getting a little bit better. Yeah, okay, so I think maybe we're back. So I was saying that the outlier detection model is a mixture model because you can have a regression for the inliers and then just some really simple model like a uniform distribution for the outliers. And I wanted to do one sort of more complicated and realistic example, which is natural language parsing. So um, if you have a sentence that looks like this, um, the rain in Spain falls namely in the plain. Bonus points to anybody who recognizes that this is a quote from My Fair Lady. Oh, and we'll add an extra, so we'll make one token for each one of these words and have an extra token for the end of sentence, which I'll just write as a period. And so we can make a parse tree that looks something like this. We have the root is always the end of sentence, and then the child of that is the main verb. The child of the verb would be the direct object, and the modifier phrase, right? And you can keep on going, right? The determiner is a child of the noun, and so forth. And so you can fill this out, and you'll get a tree whose nodes are the words of the sentence, and whose edges say what words are related to what other words. All right? And so this is what's called an unlabeled dependency tree. It's a dependency tree because the nodes are the words of the sentence instead of introducing extra nodes that say, noun phrase or something like that. And it's unlabeled because I haven't said that, for example, this is the main verb of the sentence. I've just said it's the child of the end of sentence indicator. All right, so if we wanted to learn to make a parse tree like this, what we could do is we could try and learn to classify potential edges as good or bad, meaning likely to be in the tree or not likely to be in the tree. And then we would have an optimization problem for any new sentence to determine what tree to make given all of the possible edges. So we would score all of the possible edges and then try and make a tree that includes all of the high scoring edges. And the way we could do that is to have a discrete optimization problem where there's one binary variable for every edge that's 1 if the edge is in the tree and 0 otherwise. And then you have constraints that say things like, well, if you're going to have a tree over n nodes, then you need n minus 1 edges. Or if there's any k node cycle, potential cycle, right? If there's a bunch of edges that if there are k edges that form a cycle, we can't include all k of them. We can include at most k minus 1. Right? And so we could make, and then to optimize would be just the sum of the scores of the edges that you include in the tree. So that would be a very nice discrete optimization problem. And it turns out one that in some cases we can solve efficiently. All right, so just like we talked a lot about modeling for probability distributions and for continuous optimization problems, we can talk about modeling for discrete optimization problems. And discrete optimizations are different in a bunch of ways from continuous ones, and they're also similar in a bunch of ways to continuous ones. So the way they're similar is that we often, when we build a discrete optimization problem from examples, we can have every example contribute a few constraints, a few variables, a few terms in our objective function. One way that they're different is kind of unfortunate, which is that, so you know how stochastic gradient descent will randomly pick a term in the objective to take the gradient of. There's no analog that I know of SGD. In particular, there's no algorithm I know of that can just randomly pick constraints or randomly pick terms in the objective to handle, at least not one that's as effective and widespread as SGD. And so instead, what we will do is we'll try and get speedups by sparsity, meaning that if we have terms or constraints that mention only a few variables, what we can do is propagate changes locally. And that means that just like SGD, we don't have to visit every constraint or every variable on every update. And then once we know the sparsity pattern, we need a language to describe the terms in the objective or the constraints. And one language that's really common is the language of mixed integer optimization. We'll get to another common language later below, but mixed integer optimization is a good one. And in mixed integer optimization, what we do is we represent constraints as linear either equalities or inequalities that constrain our discrete and continuous variables. And then the terms in the objective are going to be linear or convex functions of these variables. And this is actually a really surprisingly flexible language, and a lot of tools, as it turns out, a lot of pre-built tools can help optimize things that are written in this language. So speaking of tools, when you're doing discrete optimization, you should take advantage of tools. Maybe more so than continuous optimization. These are hard problems, and people have spent many years designing good heuristics for them. And so we really need to take advantage of that effort if we can. And there's two ways to take advantage of it. One is we can model the problem in whatever language they understand and pass off the whole problem to the third-party software. Or the other way is that we can write the outer loop of our optimization ourselves and then call out to one of these other optimizers. And both of those can be effective. So some types of tools to be aware of are SAT solvers. So SAT is the problem of finding a feasible assignment to a bunch of true-false random variables subject to logical constraints of the form like A or not B or C. And it's an NP hard problem, but there are very effective heuristics, and people have competitions and routinely solve problems, SAT problems that are really large. And then there are generalizations of SAT like MaxSAT, which is instead of just finding a feasible point, try and find a point that violates as few constraints as possible or satisfies as many as possible. Or you can have SAT modulo theories or sharp SAT. There are almost as many generalizations of satisfiability as there are conferences to report on them. And again, there are tools. People build these tools. They have competitions to determine the best ones. And so if you can take advantage of one of them, it's often a good idea. And then the other class of tool that I wanted to mention is mixed integer program solvers. And these are, in some sense, the the rocket gun of discrete optimization. They're really expensive, really hard to use, but they can be incredibly effective if you can use them correctly. And so these handle binary or categorical variables as well as continuous ones, arbitrary linear constraints, and arbitrary linear objective functions. And so when we talk about modeling ideas below, we can use all of them when we're setting up problems for one of these solvers. The two best known ones are Cplex and Gurobi. Both of these are very expensive, although both of them have some sort of deals if you happen to be in academia, so use them while you can. And then if you go work for a company, then the company can afford to buy it for them, buy it and solve the problems. All right. So let's get to now modeling. So one of the things that we often have to do in a discrete optimization problem is enforce a logical constraint. So a logical constraint would be something like, if you set these variables over here in this way, then this other variable over here has to be set in that way. So I mentioned the all right. Let's see, apparently I had some lag again, but I think I'm now back. So, okay, so a typical example of a constraint, logical constraint would be something like A or not B or C, right? And then if we have another logical constraint, we can write it with and it could be, let's say, not C or D, right? And if you remember, like, there are all sorts of ways to work with logical formulas like this. For example, if you do resolution on these two, you'll get the formula A or not B or D, right? And so what you would like is to be able to write out a whole bunch of these logical constraints and have your solver effectively do this sort of reasoning for you. And so in order to do that, what we can do is we can write logical constraints as inequalities on binary random variables, right? So we'll use the typical convention that true is 1 and false is 0. And then the constraint A or B is the same as saying A plus B is bigger than or equal to 1, right? Because if A is 1 and B is 0, then this is 1, the left-hand side is 1. If A is 0, B is 1, left-hand side is 1. And if they're both 1, it's 2, which is also bigger than 1. And you can do any k of n constraint the same way, right? And and or are both k of n constraints, but there are more general k of n constraints. Maybe more interestingly, we can take we can take any logical formula and turn it into linear equalities, but I'm only going to show how to do it for a particular class, which is the class that uses and, or, and not. And other connectives are basically the same thing, but it just complicates the description a bit. So this is it's good to work through an example of this yourself because it's not a difficult procedure, but like it's hard to get an intuition for what it's doing without doing it yourself. So let's suppose we have a formula, some big gigantic formula like this one down here. What we first do is push all of the knots down to the leaves by using De Morgan's laws repeatedly. As a reminder, De Morgan lets you move a knot inside an and turn it into an or of the knots, or a knot inside an or and turn it into an and of the knots. And so at the end of this, we have a formula where negations only appear at the leaves of the tree, meaning you have negated variables, but you don't have negated formulas that are larger than variables. Then at the bottom of the tree, for every variable, you either keep it. So if it's x, you put the variable x in your problem, or if it's negated, you put 1 minus x in your problem. And then every time you encounter a connective, so the only ones that are left are and or, you do all of the children first, and then you'll introduce a new temporary variable, call it t, to represent the output of your new connective. And you'll add a constraint that links the inputs of the connective to its outputs. So for example, if you have a and b and c, that's the same as saying t is less than or equal to a plus b plus c minus 2, right? And here t will be, sorry, I wrote this constraint wrong. I will fix this after class. The constraint for or is correct here, right? So t less than or equal to a plus b plus c. And so t will have to be 0 if they're all 0, and t can be 1 if any of them are 1, right? And there's a similar constraint that is not this one for and, which I'll fill in after class. And so now what we've done is we've gone up the tree, and we've substituted in constraints for each one of the connectives, and there's a temporary variable. And then at the top of the tree, we'll introduce a new temporary variable that represents the value of the root connective of the tree, the outermost expression. And in order to say that this constraint has to be satisfied, we're going to constrain that the root variable has to be true, right? That's what it means for the constraint to be satisfied. And so here's an example, right? We start from this formula, we move not inward once to get this, and then again to get that, and then we start from the bottom, and here is a good example of a constraint here. This represents here, right? So we have 1 minus b plus 1 minus d, and t is less than or equal to this, right? Which means that, again, I have to fix this constraint after class, but if it were correct, it would force t to be 0 if the and were false, and allow t to be 1 if it were true. And then here we implement the or as r less than or equal to s plus t, and then we constrain r to be bigger than or equal to 1. And so that lets us handle any logical expression with and, or, and not, and you can basically write any logical formula in terms of those connectives if you want to. So it lets you implement any logical constraint as a set of discrete inequalities. And if you want to, you can also translate circuits the same way. A circuit is basically, it's like a logical expression, except that you get to reuse the output of some of your connectives. All right, so that's logical expressions on discrete variables. We may also want to connect the discrete variables to our continuous ones. And here the typical trick is something called big M. So maybe best to explain it by an example. So here's an example. We have a continuous variable x that's constrained to be non-negative, and a binary variable z, and we say x is less than or equal to m times z. So if z is 0, then mz is 0, and x is fixed at 0. If z is 1, then mz is some huge number, because we chose a really big number m. And so x is essentially unconstrained. And so what we've done is we've conditionally set a variable x to 0 based on the value. We've conditionally set a continuous variable x to 0 based on the value of a discrete one. And there is, in fact, a general way to pick m so big that you know it doesn't matter, but that's not very satisfying because it picks a really, really big m. But often in any given problem, you can figure out how big m has to be from problem-specific considerations. And you can do the same thing. This one conditionally enforces an inequality, right? Because ax has to be less than or equal to b if z is 0, whereas ax is essentially unconstrained if z is 1 because it has to be less than some big number, b plus z times m. Let's see. I'm getting repeated constraint complaints about lag. So what I'm going to do is I'm going to stop the stream and start it again, because in the past that seems to have fixed the problem. So I'll see you guys in a few minutes. All right. So I'm back. Let's. So far, it claims that it isn't dropping any frames. So we'll see if this holds. All right. So we just finished big M. And now let's start talking about solution algorithms. So if we need to solve a discrete or mixed discrete continuous optimization problem, hill climbing is maybe the the jackknife of the algorithms. It's widely applicable. It's easy to use. It may not ever be the best tool, but it's often a pretty darn good one. So what hill climbing is we start off with some random initialization, and we repeatedly select a single variable or maybe a small group of variables, and we adjust these variables to improve our objective function. So let's say we have a maximization problem, so improve means increase. And we keep doing this as long as the objective function is still increasing. And if it stops increasing for a while, we'll restart. We'll reinitialize from our random distribution, and he'll climb again. And then at the end, we look at everything we've seen and we report the best objective value of anything we've seen. So there are a lot of variants of hill climbing. One good variant is what's called coordinate ascent, where adjust a variable to improve the objective function means maximize the objective function with respect to just that one variable while holding all of the other ones fixed. And to make it a complete algorithm, I have to say how to initialize and how to pick a variable. So let's just initialize everything uniformly at random and pick a variable uniformly at random every time we need to update one. And of course, that may not be the best, but it's a pretty general strategy. And you can often tune based on your knowledge of the problem what schedule to use to update variables. If we pick more than one variable at a time, that's called block coordinate ascent. And the optimization problem for a few variables gets harder, but we might make more progress. And so the trade-off usually depends on how efficiently we can solve the block coordinate optimization problem. So here's a problem that block coordinate ascent is good for, or actually ordinary coordinate ascent is good for. And that's the lasso problem that you've seen before, which is you have a regression loss like this. This is the sum of squared training errors, plus lambda, or a regularization term, times the one norm, the sum of absolute values of our weights. And this is a minimization problem, so it's coordinate descent as opposed to ascent. So if we hold all but one component of W fixed, we get the absolute value of that component times lambda, right? That's what's in here. All of the other components don't matter because they're fixed. And this here becomes a quadratic function of W. And so we get a single variable quadratic plus absolute value minimization problem. And it turns out that we can solve that efficiently and exactly. And so that means that we can do the coordinate descent updates efficiently in Lasso. And in fact, it's even better than that. These quadratics, they change based on the values of the other variables, but we can incrementally update the coefficients of the quadratic. And so coordinate descent for Lasso turns out to be a very efficient algorithm. And if you couple it with a good schedule for deciding which variables to update next, it can actually be competitive with the best algorithms for large-scale Lasso. So that's only sort of discrete, right? The discrete aspect comes from the discrete choice of whether to set each weight to 0. Here's maybe a more clearly discrete problem, which is k-means clustering. We mentioned this before, but I wanted to go over it in a little bit more detail. So we have a whole bunch of samples, x1 through xt, like this picture right here. And we want to pick our cluster centers, mu1 and mu2, so there's 2 of them here. More generally, there are k of them. And we assign each point to a cluster center in a way that minimizes the total, I should say, squared distance of points from their assigned centers. And so we can make a discrete variable that's 1 if and only if point I is assigned to center j. And in that case, our objective is this: the sum over points, the sum over centers, the indicator of whether that point is assigned to that center times the distance, squared distance, that you pay for in that case. And it's called k-means because if you hold the assignments fixed, the optimal value for mu is the mean of all of its assigned points. And we can solve k-means with block coordinate ascent. In fact, that's a really good algorithm for it. What block coordinate ascent means, we assign every point to its closest cluster center. That's optimizing over the z's. And then we update each cluster center to be the mean of its assigned points. That's optimizing over the mu's. All right, so that's coordinate ascent. Another variant of hill climbing is what's called stochastic hill climbing. And in this variant, instead of fully optimizing the variables that we pick. We just randomly perturb them. And then if the perturbation makes our objective better, we keep it. And if it makes it worse, we discard it and then pick another variable to optimize. So in comparison with coordinate ascent, it's potentially a whole lot faster to just perturb a variable than it is to optimize it. Especially if you pick whole groups of variables at once, it can be much faster to perturb them than optimize them. But obviously we don't make as much progress with each step because we're not optimizing. And so the trade-off is typically that if it's expensive to do the block optimization, maybe it's better to do stochastic hill climbing and just perturb it. Whereas if we can do the optimization cheaply, it's often better just to do that optimization. All right. So that's hill climbing. I want to mention another algorithm as well, but to do that, I have to mention a more general problem. And that problem is one that we come across a lot, which is probabilistic inference. So we start with some probability distribution over a whole bunch of variables, and then we condition on some of those variables. Let's say C is the indices of the variables we condition on. Then we marginalize out some of the other variables, so M is the indices of the ones we want to get rid of, and then O for optimize is the set of variables that we want to maximize over. And so we want to max over x sub O, the sum over all values of x sub M, of the probability of xo and xm given xc. And this, you can think of this as being very much like a constrained optimization problem, because if we have a factor graph for this distribution, each one of the factors is a soft or hard constraint that links several of the variables. So if we take k-means and turn it into the probabilistic version of k-means, meaning that we say that the distance from a point to its center is a Gaussian random variable, and the assignment of a point to a center is a categorical random variable, then we'll have a prior distribution over the mu's and z's, and then when we condition on the x's, we'll have a posterior distribution over the mu's and the z's. And if we make the simplest possible assumption that we have a uniform prior probability for the mu's and the z's, we get this as our log likelihood. So it's essentially exactly the k-means objective, scaled by the variance that we expect for these guys, and offset by a constant that doesn't matter for optimization. And so if we were to maximize over the z's and the mu's, right, we would get back k-means. But since we now have this probabilistic interpretation, we can ask to marginalize out the z's and then maximize over the mu's, and that would be a probabilistic inference problem. Missing data is another good one. If we make a joint model of a bunch of variables given some parameters, we can and if some of our examples have missing data, we can try and make a joint model with parameters theta for these variables, but then we can't fit it directly by maximum likelihood. We first have to marginalize out the missing variables before we then do maximum likelihood. All right, so hill climbing, stochastic hill climbing, coordinate ascent, they all work really well if there's no variables to marginalize. If there are variables to marginalize, we need another method. And so I wanted to give you at least one method for that more difficult case, and that method is based on Gibbs sampling. So what is Gibbs sampling? Let's start from the case where we don't have to optimize over any variables. In that case, what Gibbs sampling is doing is just trying to tell you what is the distribution of the variables we're marginalizing over so that we can do that marginalization. And the way it works is we repeatedly pick one of the variables in x sub m and set it to be a sample from its conditional distribution given the remaining variables. So for example, in the Gaussian mixture model, the conditional distribution of one of the means is Gaussian with mean equal to the mean of all of the training points assigned to that example, right? So this is counting the number of points assigned, and this is summing up all of the points that are assigned, so the ratio is the mean. And then the variance depends on how many points are assigned to that cluster. And it's also not hard to calculate that the conditional distribution of one of the indicators is proportional to how far the corresponding point is from the corresponding center. So if you're as the point gets farther away from the center, it becomes less and less likely to be assigned to it, and it does that really quickly, right? E to the minus something squared. So Gibbs sampling would just be to alternate in blocks. We resample the examples by, resample the cluster memberships by picking an example and updating Zij for all j, and then we run through the clusters and resample the mu's for that cluster. And that would be the analog of the block hill climbing for clustering. But now what we're doing is sampling, or trying to sample from the this distribution. All right. So Gibbs sampling has a nice guarantee, which is that if we run it, we actually get this distribution we were trying to get. So in the limit, the distribution of xm on any large enough iteration is equal to that conditional probability. And when that happens, we say that the sampler has converged or has mixed. There's no general way to test for convergence, unfortunately. So people have a bunch of heuristic ways to do that. Probably the most common is to use diagnostics to tell whether you have converged or not. One diagnostic, for example, is to make a plot of the probability of the current setting of the variables, right? And so what will happen is, the probability or the log probability will be, so we'll graph with iteration, and this is log p, and we'll start at some low value and we'll go up and down and up and down and down and up, right? And it'll generally trend upward, but it'll be random because Gibbs sampling is random, right? And then at some point, right, it will level off, and there will be no trend, right? And so at this point, it looks more or less like we've converged, whereas here we clearly have not. Right, so that's one diagnostic. Another diagnostic is to look at the autocorrelation of the settings to any given variable. The autocorrelation is just the correlation of that variable with its setting k iterations later. And if things are going well, the autocorrelation will be low once you get past a certain distance, a certain lag. If things are going poorly, the autocorrelation will remain high. And if that's the case, then that just means you're stuck. You have to run the sampler for a really long time. All right? And so we run our Gibbs sampler. At some point, it's mixed, and then after that, we can keep looking at it and taking samples every so often to get more and more samples from this conditional distribution. All right, so that's Gibbs sampling. On its own, it's already a useful tool. But if we want to optimize, what we can do is we can run a Gibbs sampler. So now we have XO is not empty, so we have both XO and XM. And we want to sample from their distribution. And we run a Gibbs sampler where we pick variables in either of those two sets repeatedly. And then we run and we let it converge, and we collect a bunch of samples like that. Then, for any new value XO, we can approximate its probability as the average over these examples of the probability when we fill in the marginal value from that example. And so what that means then is that we can use this as the objective for a hill climbing run or any other optimization strategy. Right? So for example, we could fill in missing data with a Gibbs sampler, right? We just randomly sample both the parameters of our model and the missing data, and that will get us the marginal distribution of the model parameters and the missing data given what we've observed. And then we could take that. We could take the distribution over model parameters as like a model combination, a model average, right? But if we want just a single model that's optimized, maximum likelihood, we can then fill in what we sampled for the missing data, and that basically just creates some new complete data training examples, and we train on the complete data training examples instead of the original missing ones, and that lets us solve an ordinary maximum likelihood problem for our parameters. All right, so that was all I wanted to say about discrete optimization. So what I would like now is to switch to answering questions. I see there's already a couple of questions posted, so people can continue posting questions if they like, and I'll go ahead to answer questions like this one. Let's see. So let's see. So the question is how to deal with dummy coding for a feature like zip code. And that's a good question because if you have zip code, there are thousands and thousands of different zip codes in the U.S. And so if you dummy code them, then you're going to have a model with those thousands and thousands of parameters. And I guess there are two answers to that question. Depending on whether it's something like zip code, where you know a little bit more about each one of the zip codes, or whether it's something where you really have no idea ahead of time what the variable means. And if you have no idea ahead of time what the variable means, you're basically stuck needing a lot of data, right? So you've got to, if you've got a categorical variable with thousands of settings, you need to see each one of those settings at least a few times to know what it means, what its what its statistical behavior is. On the other hand, for zip codes, we know a lot about zip codes, right? So we can, instead of having that categorical variable, we can replace it with some other features. Like we could have features based on geographic location or climate or rural versus city, right? Like there's a whole bunch of features that we could include based on the zip code that are not just the dummy code for the zip code. And if we don't have much data, we should pretty much always use the sort of more interpretable features instead of trying to learn something separate for each one of the zip codes. Now, if we have unsupervised data available as well, we can do something in between. So an example of that is word2vec. So if you look at words, right, there are at least 10,000, maybe 100,000 words in any reasonable vocabulary. And instead of trying to use a dummy code for each possible word, which people do if they have enough data, but if you don't have enough data, you can't do that. So instead of having that dummy code, what they'll do is they'll try to use unsupervised data to learn features of the word. And so what word2vec does is it learns features based on what words tend to co-occur with the word in question. And then you can get a low-dimensional feature vector that contains most of the information of your high-dimensional categorical variable. All right, another question about Piazza and Q&A, whether you guys are going to still have access after the class ends. That is my intent. The Piazza company might go out of business, or the server for Q&A might crash and burn, but it's our intent to keep Q&A and Piazza up. So I don't see any more. I don't see any more questions on Piazza. And the TAs have not posted any questions for me that people have texted to them. So I think probably the best thing to do is to stop and do office hours. So as a reminder, I am in Spain. So do not go knock on my office door in Pittsburgh or you will be disappointed. Um, but I will be available via Hangouts, either to text or video chat if anybody has any questions. As another reminder, 2 days from now is your final exam. We posted what it's going to be like, the description of the exam on Piazza. But if you have any concerns or questions about that, please let us know as well. All right, so thanks very much. It's been a fun class, and I will hopefully hear from everybody as they're asking tons of questions about the exam. Talk to you guys later.